So in this fragment, I'm going to touch base upon the properties of complex number based on the Moivre's theorem. So as we learned about in the previous fragment about how do you convert from in the Cartesian to Euler's form. So if I take, let's say, z1 as r1 e to the power theta 1 and z2 as r2 e to the power theta 2I, and if I multiply them, you can see the modulus get multiplied and argument get added because the powers get added. So for example, if I got a complex number z1 and z2 as this, and if I multiply, modulus gets multiplied and the argument get added. So the resulting complex number is going to have an argument of pi by 12 and modulus as 2 root 2. And when you divide two complex numbers, the modulus get divided and argument gets subtracted. And when you raise a complex number to certain power, the modulus gets raised to power n and argument gets multiplied by power n by n. So if I have z is r cis theta, z to the power n is r to the power n cis n theta. So this is referred as also de Moivre's theorem. So now let's just take some more examples on de Moivre's theorem. So I'm just going to quickly touch base upon one example where it covers the properties of addition of arguments. You can see here, if I multiply into complex numbers, the modulus gets multiplied and argument get added. Here it's getting multiplied and divided, and argument is getting subtracted. So these are the basic properties of the arguments. So here's the DP question about the basic properties of modulus or argument. Now, for example, if z1 is 2 cis 150 and z2 is negative 1 plus I, calculate z1 over z2 in both modulus and argument form. So of course, z1 is 2 cis 150. I can add on 2 cos 150 plus I sine 150. Then that is 2 times negative root 3 over 2 plus I times a half. If you don't know how to find out cos 150, cos 150 is actually here, which is, this is 150. So actually this is 30 degrees. So cos 150 is same as cos 30, but that's going to be negative because it's on second quadrant. So that's how I got this. And sine 150 is same as sine 30, which is positive half. So that's how I get this. The next up is express z1 over z2 in this form, modulus and argument, and Cartesian form. Now, since I got both the complex number in either of the forms, I can do that. So let's have a look at how do we do it. So when I divide the complex numbers, z1 over z2, it is modulus get divided and argument gets subtracted. You can see I subtract 150 minus 135. So 2 over root 2 is root 2. And also the other way to do is that z1 over z2. So the z1 is actually this and z2 is actually this. And when you divide them and rationalize them, you get this. So this is very interesting if you can do it manually, like you can see whether you're getting this or not. Now they say that last part is using the result, find out the exact value of tan 75. So since I got here that it's the same complex numbers written in two format, this is also same as root 2 cos 15 and plus root 2 sine 15i. So what I do is I take this as the real part and this is the imaginary part. So from here I get tan 15. If I divide these two relations, this over this and this over this 2 and 2 get cancelled, and you get this. So sine 15 over cos 15 actually, so this negative over this positive. And if you rationalize this, you get the value of tan 15. And they asked us to actually find out tan 75. So tan 75 I can write down as tan 90 minus 15, which is basically, I can say cot 15, which is also 1 over tan 15. So if you just link up this part, that is going to help you pretty well. So this is one of the DP question. And if you rationalize this, you get the final answer as here. So this is the property of the basic property of modulus and argument. And I'm going to just now cover up some questions on de Moivre's theorem. All right, so this is a question from Fabio, one of the textbook for DP. Now, the question is that if z is cis theta, show that z squared is cos 2 theta plus I sine 2 theta, and the similar expression is this. So what they are basically trying to do is that if z is cis theta, so If z is cis theta, you go two ways. Okay, so one, you use de Moivre's theorem, which is straight away that if you square a complex number, the argument gets squared. Here, obviously, the modulus is 1. You can see 1 cis 0, 1 cis theta. So modulus gets squared and argument get doubled. So here, straight away, one path is to find out that, which is cos 2 theta plus I sine 2 theta. So I sine 2 theta. Now, the second fragment that they wanted us to do is this, which is interesting. What I'm going to do is I'm going to normally expand this using binomial expansion. So cos theta plus I sine theta, the whole square, if I expand it, a square plus twice ab plus b square. And if I collect the real part is this, and imaginary part is this. So that's the first part proven. And now this is that hence show that sine 2 theta is this, cos 2 theta is this, and tan 2 theta is this. So now since he got the real part of the complex number is cos 2 theta, that must be equals to this, which is cos square theta minus sine square theta. And sine 2 theta, which you got is here, is basically the imaginary part. So imaginary part must be equals to this. So what happened is that if you equate the real part with real part and imaginary with imaginary, you get the desired simplification. Now the next part they said that show the tan 2 theta is this. So that I have done it. In case if you have any doubts, you can just cross check. Now the next part is using similar expression, find out the values in this term. And these are indeed the identities of, like we call triple angle formulas. So let's just do this part. So what I'm going to do is here I'm going to expand cos theta plus I sine theta the whole cube using the binomial expansion. In case if you're not clear about a plus b the whole cube formula, it's a cube plus 3a square b plus 3ab square plus b cube. So cos theta plus I sine theta, the whole cube is actually this. So if I take cos cube theta, and this is the real part and this is the imaginary part. So if I take the de Moivre's theorem, if I raise a complex number to the power of 3, argument get tripled. So that is cos 3 theta plus I sine 3 theta. So what we got is here. So cos 3 theta is basically equals to this, and sine 3 theta equals to this, which is imaginary part. And if you notice that there is a sine square theta that I need to get rid here of, and here is cos square theta. So if I get rid of sine square theta, I get 1 minus cos square theta, because sine square theta plus cos square theta is 1. And if you make either of the subject, we get the expression that we wanted. So I'm just going to quickly go over this. So here we go. So I simplify this and put the, instead of sine square, I put cos square, 1 minus cos square. Instead of cos square, I put 1 minus sine square to get the expression purely in terms of cos, and here purely in terms of sine. And of course, to do tan 3 theta, you got to divide them and use the logic. I'm just going to show it to you here quickly, the expressions here. So how to do this in terms of the tan 3 theta.